Welcome to everyone's not favorite new game, Digital Control for Power Electronics Bingo! All right, folks, on your board today, you will find the following squares: blue smoke, fingers crossed, fried components, creeping bugs, testing, more testing, and even more testing. And don't forget your free space! Okay, no, we're not actually playing bingo today, although I am sure some of you have played a similar game. Even though it's funny to joke about, blue smoke really isn't that fun. Sure, we want insight into our systems and the flexibility and adaptability that goes along with digital power control, but before we take that big step, maybe we should simulate it first. Hi, I'm Amelia Dalton, host of Chalk Talk. Yes, simulation has a lot of different benefits, but today we're talking about simulation-based tuning of digital power electronics controllers, so we can avoid that whole bingo business altogether. My guest is Arkadiy Turevskiy, and we've got a lot to cover, so let's get started, and don't forget to mark that free space. And before we get started, don't forget to click that link. There you can find even more information about this topic. Welcome, Arkadiy. Thank you so much for joining me.
Thanks for having me, Amelia. That's great to be here.
Okay, so most of us will already know why we need digital control for power electronics, but let's quickly recap why exactly that is.
Right. Motor control went digital years ago. We see the transition from analog to digital in power conversion control now, where the sampling rates are typically much faster. The main reasons for why we see people going to digital control are flexibility and adaptability. And what this means is that you can change your controller by changing the software, something that is impossible to do when it's implemented with an analog circuit. If there are any problems, you can change the code. Also, more advanced control logic, so things like gain scheduling, maybe feed-forward control, or some sort of adaptive control. That's all really difficult to do with an analog control, but is easy with a digital control where you just write code to implement it. So additionally, we see that the cost of microcontrollers and FPGAs is continuing to come down, and at the same time, they're becoming more powerful. And so that again makes digital control more viable and more attractive option for control system designers.
Now, simulation has a lot of benefits in this realm, right? It's better than crossing our fingers and hoping for the best.
Yeah, absolutely. I think the first time you start your test, your power electronic system, you don't want to fry it. You want to have some confidence that the testing will go as planned. And the way to do it is to use simulation. And so by building simulation models, by testing different scenarios in simulation, you can build confidence that your controller will work as expected. You can also find bugs that always creep up and are unexpected, and you can fix them in simulation instead of discovering a bug on the actual systems that you're using to test, or even worse, in the field when a customer calls you and informs you about it.
Right. Okay, so let's talk about tuning that controller.
Yes, we'll talk about this particular aspect of simulation today. There are many other benefits of simulation that we'll touch upon later, but one benefit is that it also enables control system designers to be more systematic about how they tune their control system gains. So a little bit of a narrow focus in our conversation today, but I hope it will be interesting for people who are involved in tuning those control systems. Just as with traditional way, when maybe you just write the code, deploy it to your target, connect to your actual hardware, and then start testing, one thing you could do is just try a different set of gains, see how well the system works. You can definitely do that in simulation as well. If you have a simulation model of your motor or power converter, you can try a set of gains, run a simulation model, see if you're close to meeting design requirements. If not, adjust the gain somehow, run the simulation again. This can be a time-consuming process. You're doing some sort of guessing here, doing ad hoc iterations on how to change the gains. With simulation models, you can be a little bit more systematic than that, and that's what I really want to show here. And so we'll talk about 4 different methods for how to use simulation to tune controllers. They're listed on the slide. 2 of these methods are, I think, methods that a lot of people are familiar with, and 2 two other ones are more specific capabilities that we developed at MathWorks, and I hope they will be interesting for people to learn about.
Okay, so let's tack that first method, average models.
Right, so what that means in the context of power electronic systems is that those systems we have components such as, an IGBT that you see in the picture here, or diodes. For us control system designers, those are essentially switches, so they can be on or off. And depending on the position of the switch, on or off, the system dynamics is changing. And so one thing we could do is to try to approximate this generally nonlinear dynamics with a linear system. And the way we could do it is by looking at dynamics of our system when the switch is on and when the switch is off. For each of those two operating regimes, modes, the dynamics is linear. And so if you take these two sets of, if you wish, transfer functions and average them, we get what's called an average model or a small signal model. And we can use those models, which are essentially state space systems or transfer functions, to design our control systems. And we at MathWorks provide a lot of tools that can help you with designing controllers for systems that are represented by transfer functions. So in the pictures that we see here, we have a power electronic circuit. We know that the small signal model for that is a transfer function, and based on the values of capacitor, resistor, and inductor, we can figure out what the coefficients in that transfer function are, and then we can use that transfer function to interactively shape the loop of our system to meet the gain margin and phase margin requirements and bandwidth, and look at the overshoot and so on and so forth. So that's what the average models are.
Okay, now AC sweep was next, right?
Yeah, AC sweep is another industry standard technique. And so why would you use AC sweep if you can have this, average value models? The problem is that these average value models are known, they're studied for many known and simpler topologies. So if you have a boost converter that you need to control or a buck converter, those are well studied, you know what the average value model for those is. If you're looking at a different topology, it can be more difficult to derive those average value models. And so then people turn to this AC sweep method, where you take the simulation model that has switching elements in them, IGBTs, MOSFETs, diodes, and you try to get a linear representation of system dynamics by injecting an excitation signal into the model, logging the output from the system, and using that data to compute the frequency response of the model in the frequency range of interest. And the way you do it typically is you inject sine waves at different frequencies, or one sine wave where the frequency content is changing over time, and that would be called a chirp signal. So let's maybe take a look and see how that works.
Sounds great.
Okay, so we'll be using a boost converter model that we see here. Before we start the demo, we'll mention that we will be interested in controlling the output voltage of this boost converter. We want to maintain it, keep it constant as the input voltage is changing or the load resistance is changing. And so for that, we will need to design a controller that will change the duty cycle to maintain the desired output voltage. So the dynamics that we're interested in is shown here, from duty cycle to the output voltage. So let's now see how this works. So here we have a simulation model. We specify that we want to inject an excitation signal at the duty cycle and log the output at the output voltage. We start the tool where we can specify the excitation signal, in this case a sine stream, a set of sine waves. We specify the frequency range of interest, the number of points in that frequency range of interest. And for each sine wave, we specify the amplitude that has to be small enough to keep us in the linear region of operation. And then we just run the simulation and ask the tool to compute the frequency response. We see the simulation is running, we look at the output voltage, we see how the frequency content is changing, the frequency is increasing. When the simulation is done, the tool automatically computes the frequency response for us. We can bring this frequency response into MATLAB. We see complex numbers here. And then we can start our control design tool called Control System Designer, where we can interactively shape the loop. We start by bringing this frequency response in. We see it here in the body plot. We can add an integrator. We can start changing the gain of the system. We can add the compensation elements such as lead or lag For those elements, we can interactively adjust the location of the pole or zero. We can again change the gain of the system. And as we're doing that, we can observe how the crossover frequency is changing and how the gain and phase margin are changing. You see it in the lower corner of those plots. So that's the method that you would follow if you're doing the AC sweep.
Okay, so let's talk about system identification and PID tuning.
Right. So there are many different methods that I'm talking about here, right? So this next one is something that we developed at MathWorks, and the whole idea is to just simplify this whole process, make it a little bit easier. And so here we know that, a lot of times the compensation that people are using is some sort of PID controller, maybe PI controller. We wanted to provide a more efficient approach, easier approach for tuning the gains of PI controllers or PID controllers for power electronic systems. What we're doing here is something very similar to the AC sweep. The difference is that now we are not going to be injecting a set of sine waves. The problem with sine waves is that if you don't specify the right frequency range, for example, if you specify the frequencies that are unnecessarily low, then the simulation will take a very long time because these are systems with switching. Sampling rates need to be very high to capture the dynamics of the systems, and the combination of very small sample steps for simulation and low frequencies that you might be estimating dynamics at can lead to very long simulation times. So we thought that we would provide a better way to do it, and therefore this approach with system identification and PID tuning. So here we take a simulation model, we inject an excitation signal. In this case, it's not typically a sine wave, but a step. We inject a step into the signal, and we run the simulation twice. Once with a step injected, and another time with no excitation signal added to the system. The difference between these two simulation runs will show us the response of the system to the step signal. And from that response, we estimate the transfer function of the system dynamics using system identification approach. So we are not just estimating the frequency response, a set of complex numbers, but we're estimating a transfer function. And then we have a tool, PID tuner, that can take this transfer function and automatically compute a set of PID gains based on this transfer function. Let's see how this works.
Okay.
All right. So here's a model of a buck converter. We already simulated it with default set of gains. We see the response is not great. We have a lot of oscillations. Okay, we have a disturbance here in the system shown in the lower right subplot. And we have a PID controller that's doing the control. The gains are not set properly. They're just at some random default values. So we start by pressing the tune button, and then we say identify a new plant. So we'll get the transfer function of the model by simulating the system. We specify the sampling time, the offset, the amplitude of the step signal. All these parameters are explained in detail, and then we run the simulation. So I know I'm going a little fast. I just want to show you quickly how it works. We have extensive docs that covers in detail how all of that works. So we run the simulation twice. From the difference of the two runs, we get the system response. And that's what is shown now in the plot on the right. And now we start feeding the model to this response. We can choose the type of transfer function. It can have one pole, two real poles, two underdamped poles. Once we select the structure, we can interactively change the parameters of this transfer function to try to fit the observed system response, or we can let the tool do it automatically. And then we have the parameters here of the transfer function, and we can just use this transfer function with the PID tuner, which just automatically tunes PID controller gains, and we can adjust the response to make it faster or a little bit more stable. And once we're happy, we just write those calculated PID gains to our controller and run the simulation and hopefully observe much better controller response. In this case, we see there is still a little bit of overshoot, and so we'll deal with that by enabling anti-wind-up logic. Okay, in this case, so we'll specify the limits on the duty cycle. We'll specify that we want anti-wind-up protection, rerun the simulation, and see that we effectively eliminated the overshoot. So that's very briefly the overview of how this PID tuner with system identification approach works.
Excellent. So let's talk about that last one, PID Autotuner.
Yeah, I know it's probably getting confusing, a lot of different methods here. I hope you like this last one because I think it's the easiest one to use. And hopefully when you see it, you will think so too. Okay, the idea here is to really simplify this approach that we saw now even further. So again, it works for tuning PID controllers, and let's see how it works in simulation. Okay. So again, the same simulation model with the same bad initial set of gains. Again, we go into the controller subsystem. We have our PID controller block with this default gains. And now we'll select frequency response base, that's what we call it, tuning method, and press the tune button. And now here we specify the experiment. When do we want to start the experiment? How long it should be? The amplitude of the excitation signal, and the desired target bandwidth. That's really all we need to do here. The tool does the rest automatically. If you're wondering how we set those parameters in the dialog, again, that's all documented very well, so you can read that, learn more about it. But now when we are done, it tool runs the simulations automatically, 2 simulations, and from the difference of those 2 runs, it automatically computes the system frequency response and automatically computes PID gains. So there are even fewer steps for you as a user to do. Now we have a set of calculated gains. You saw that it's really fast. We just update the block with those calculated gain values. We can see them here. And now all that we really need to do is run our simulation model and test that we get the expected results with better controller performance. And that's what we see here. Now, the really interesting thing here, I think, is that this method can be used not only on simulation models like we did here, but it can also be used on the actual hardware. So this algorithm that injects an excitation signal, runs it through the system, collects the output data, and then computes PID gains, it can work in real time. And the way we do it is that we can actually generate code from this algorithm and deploy it to the actual embedded system. And so even if you don't have a simulation model of your actual system, you can try this PID Autotuner on your actual hardware and get the better PID controller gains.
Very cool. All right, so there are a lot of other things simulation models can be used for, right?
Most definitely. So I'm a controls engineer, so I wanted to bore you to death with different methods for how to use simulation for tuning controllers. But yeah, definitely there are a lot of other uses for simulation models. People use simulation models to size components. How do you choose as passive element values to minimize ripple in your system? How do you size your heatsink so you can use simulation models to estimate losses, conduction and switching losses in your system? In addition to feedback logic, there is definitely a lot of logic that goes into the controller that can deal with faults, that can deal with different modes of operation. And so simulation can be used to design this logic and, more importantly, probably test it to make sure that it's working as expected. You can inject faults into your system, as we said, and test that the controller is providing the expected response. And these things can be really tricky and dangerous to test on the actual hardware, right? You can imagine. Typically, our system will need to operate at different conditions. So for something as simple as a boost converter, it can be different input voltages or different load scenarios. And so we can run simulations at different operating conditions, make sure that the system is working as expected. We can also use simulation for real-time testing, where we can take the simulation model of our plant, of our power electronic system, generate code from it, and run our controller that's running on the embedded microcontroller or FPGA against this real-time plant model. And that's called hardware-in-the-loop testing. So you test the controller in real time now, how all the real-time operation is happening. And then another good benefit is that for the controllers that you designed in simulation, it's working as you expected. Instead of handing it off to somebody who would go and manually write the C or HDL, And it's especially difficult with HDL to just write this. Not a lot of people know how to do it. We can actually automatically generate this C or HDL code for you, and you can just download it to your microcontroller or FPGA and run with it.
Nice.
We actually have a paper, if you're interested to learn more, that describes all that in a lot more detail and talks about other benefits of simulation for power electronics control.
All right. Arkadiy, where should my audience go for more information?
So our tools are used in a lot of areas, but for power electronics specifically, we put this nice page, we think, together. You call it motor and power control. And there we link to different pages that talk about how our tools can be used for specific things in power electronics control, like doing field-oriented control for motors or MPPT algorithms, or simulating boost and buck converters, or designing controllers for BLDC motors. You'll find plenty of examples that talk about how to model systems, how to design and simulate controllers, how to generate code for real-time testing and implementation. You'll find information about various products and also, I think interestingly, testimonials from customers that use the tools, and they describe the type of systems they were trying to design, how they used our tools, and how our tools help them.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me.
Thanks for listening to me and for learning about all these methods for tuning control systems. I hope one of them will be interesting enough for you to try.
And before we go, you didn't forget to click that link, did you? There you can find out more information about simulation-based tuning of digital power electronics from MathWorks. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of eejournal.com or check out YouTube, keyword EE Journal.